All right, so I did have one email get sent in, and I do want to clarify it, and I'm going to try to update the worksheets today. There is a comment on the lab worksheet this week about the KD, the partition coefficient. That's actually because when I make these worksheets, because there's a lot of formatting that goes in the background to make these accessible with ADA compliance, I have a hot habit of copying and pasting things over, and when I did this lab, I copied and pasted it from a previous lab. So you're just kind of seeing the KD because I forgot to delete it out. So definitely what I'm going to plan today is to update it so this way those of you in the Thursday lab, when you download the worksheet, it doesn't have the KD in there anymore. And for those of you who've already done the Monday, Tuesday Organic 1 lab, the worksheet will be updated by this afternoon. But that's the only question I received this morning. So are there any questions from those of you watching the video right now? So you're not going to determine, so a question has been asked in the lab, we have to make a flow chart and determine pKa. You don't have to determine pKa, go look it up, we have tables for it, but you do need to make a flow chart. The big reason is that you're going to end up with 3 solutions, A, B, and C, and you need to be able to intuit basically what each solution contains. So you've got 3 compounds, benzoic acid, naphthol, and para-dimethoxybenzene. One of those will end up in each solution. Solution A will contain one compound, B will contain another, C will contain another, and you need to know which one is which based on the chemistry. Now, a hint in this regard, water has a pKa of 7. So anything lower than 7 is a better acid than water. Anything higher than 7 is a better base than water. All right. Next question, can we go over J coupling? Anything in specific, or like start from base, the theory, and how it affects NMR spectra? And while I wait for your response, let me go grab my gyro. One more thing. The whole thing. Okay, so to understand J coupling, the first thing we have to understand is NMR. So NMR, we're not going to use the North Pole, South Pole analogy. We're looking at nuclear spin, and we're going to look at it from where that name came from, which is spin. So spin here is going to refer to angular momentum. So what happens is we have nuclei that basically look like they're spinning tops. And what happens in the NMR is that their angular momentum is aligned with the magnetic field. All right, I'll get to your question in a minute, Elijah, because I don't know how much longer this top's going to spin. So what happens in the magnetic field is we're going to tip it 90 degrees, and when we do that, you're going to behave today? You don't feel like you're going to behave today. Let me answer Elijah's question first. I'll get this top set back up. A quick question lab, that will be all today. All right, Elijah, what's your quick question? Oh, hi, Squeaky. Yes, the top does serve a purpose. So as we have our nucleus spinning in the magnetic field, when we tip it, yes, there's a cat. Actually, I have a cat. And right now she's trying to get attention. So this is the way the top wants to spin. When we knock it 90 degrees, come on, behave. It's going to do this. It's going to rotate around in a circle. So when we knock it, what's called the 90-degree pulse. So H here is our magnetic field. When we have our nucleus and we knock it 90 degrees, it will begin to rotate perpendicular to the magnetic field. Now, electron does have a net magnetization. So while this nucleus is spinning, we've got a detector, which is a radio frequency coil, and what it picks up on is the magnetization of the electron as it rotates. So it'll push electrons one way and it'll push the other, and we end up getting a signal that looks like a sine wave. So this is what happens for a nucleus that's acting by itself. And when we take a Fourier transform of this, so we've got time versus intensity, when we do a mathematical transformation, we end up getting a frequency associated with it. So this is the basis of NMR. This is what nuclei do in the magnetic field. Now, this assumes the nucleus is purely by itself, meaning that it doesn't have any other nuclei that are the same isotope and element. So something like a carbon atom and a hydrogen atom will both interact with the magnetic field, but because they have different frequencies at which they rotate around, they don't interact. But if we have two hydrogen atoms, so let's say we have this difluoro complex with two hydrogens on the side. Both of these 1H nuclei, the one hydrogen nuclei, have the same frequency, and when they tip at 90 degrees, their angular momentum can be working clockwise or counterclockwise. So there's a 50-50 chance that they'll have the same rotation and a 50-50 chance that they'll have opposite rotations. Well, this has an effect on the chemical shift, because if they're rotating together, they reinforce each other, so that makes them less de-shielded. If they're opposing, they have opposite angular momentum, so they oppose each other, and that increases the chemical shift. So for this nucleus, because keep in mind, we're drawing one molecule, but this is going on with tens of millions of billions of atoms. So in a given NMR experiment, we only need roughly 1 to the 10 to the -4th or 10 to the -5th nuclei to get enough signal. So we're dealing with a statistical distribution of atoms. We're going to get two signals. One for molecules where this hydrogen is seeing this one spin clock, having the same angular momentum, and one where they're having opposite angular momentums. So when we think about chemical shifts in NMR, the way I was taught is that you have the H here is what's called the Hamiltonian. It's what dictates the energy which gives rise to the frequency that we measure. The first one is the chemical shift. And that's what's going to do the most for what signal we see. Basically, what does the environment of the given nucleus look like? So in the case of being around two fluorines, this is going to be really de-shielded. I'm going to draw this as a red hydrogen. So with hydrogen, we have 0 to 10 ppm. So the blue hydrogen here is going to be around something like 4 parts per million. So the next thing for nuclei is going to be the J coupling. So in this case, we have a scenario where this hydrogen have different spins. And when we say spins, we mean alignments, not like spin 1/2. And then we have another where they have the same. For this hydrogen, it's going to have a chemical shift closer to about 2 ppm. And we're going to see the same thing where it sees, half of them see a hydrogen that is with the same spin, one other half see a hydrogen that have an opposite spin, angular momentum. So to answer Elijah's questions really quick, actually you used 3 grams. The material should have been a 1-to-1 ratio, so your percent recovery should have been 1 gram for each. So J coupling occurs because the nuclei have angular momentums that are going in either the same or different directions. So if we have one nuclei here, one hydrogen here, and one hydrogen here, they each see this effect. So when we measure this hydrogen, we see the effect of it being spinning the same way as this hydrogen, and opposite ways as this hydrogen. And the same thing for the red hydrogen. We see the effect of it being aligned with this one and going opposite this one. How do you know the ppms? We look them up in tables. So For proton NMR, 1H NMR, the range is typically -2 to 10 ppm. For carbon, it's -50 to 200. There is a complicated physics behind where that frequency range comes from, but you don't really need to know that. But again, there are tables. Actually, if you go to the course website, I think it's under the test one material, there's tables of physical properties. In there are listed common chemical shifts, these ppms. Yes, you are allowed to use the table characterization values for the exams because there's really no point in memorizing these. And I say that because there are a lot of nuclei that there are a lot of functional groups that share chemical shifts. So something like a CH2 is slightly more deshielded than a CH3, but that depends on what's bound to the CH2. It's also what depends on what's bound to the CH3. If you have a CH3 bound to a fluorine versus a CH2 along and just a pure alkane that's carbons and hydrogens, the CH3 in that case is actually going to have a further deshielded shift. So you're correct, Elijah. It's for recovered solid mass divided by 1 gram. So what happens if we have 2 hydrogens? Well, we have to consider the case of this one and consider the case of these two. Now, for these two, they're not going to interact with each other. And the reason they're not going to interact with each other is they had the exact same frequency. So we're only going to see this effect if we have a reason to believe that the nuclei have a different frequency. You're welcome, Elijah. And basically, this is where we get the idea that each functional group is going to have its own chemical shift because there's no reason to think the hydrogens within that group have different chemical shifts. The exception to this being if it's a chiral molecule and they're not meso. So if it's a hydrogen on a chiral atom, it will have a different chemical shift depending on the chirality. We are not going into that level of depth in this course. That is a very hard concept to work on. But I am going to put that caveat on there is that if you have hydrogen atoms on a given nucleus, it should be one fixed chemical shift. But anyway, if we look at these two, we're going to see twice the signal because there are twice as many hydrogens, but we're still going to see the split, the doublet. And the doublet's going to come from the fact that you've got where these two have opposite directions, so -1/2 and 1/2, and one where they have the same direction, 1/2 and 1/2. How about the 4 ppm? Well, we have 4 possibilities. One possibility is that, let's say we're going to treat this as having a spin 1/2. Both of these are spin -1/2. And then we have 2 situations one where there's one spinning one way, one spinning the other way, and there's 2 possibilities because we have 2 hydrogens, and then we have the other one where they're both spinning in the same direction. So we're going to get 3 peaks. And the 3 peaks correspond to where they're both going opposite the nucleus, the 2 scenarios where they're going, one's opposed, one's with it, and the one where they're both going with it. But because we have 2 possibilities, this is going to end up having twice the peak height. So we're going to get this triplet pattern. Now, if this had 4 hydrogens, we'd see the same. We'd see it break into a pattern of 4 splitting patterns. So your splitting pattern is always the number of hydrogens plus 1. So if you have 2 neighboring hydrogens, you get a triplet. If you have 1 neighboring hydrogen, you get a doublet. If you have 3 neighboring hydrogens, you get a quartet. Now, how does this change if we've got this hydrogen and we have, unfortunately, I think I got a little bit of life left in my black pen. We have 2 other hydrogens. Well, this is where it's going to get tricky. There is a width associated with these splits. And this is what's called the J coupling constant. So the J coupling constant describes how far apart these shifts are, and they depend on the bonding environment of these hydrogens. if the bonding environments are the same, meaning that if we looked at this molecule and the ones on the right and the ones on the left basically are the same chain, have the same chemical form and everything, it's the same J coupling constant. So we would still only get a triplet pattern because they're splitting them just as much. Now, if they're not the same bonding environment, meaning that instead of a CH3, this is something like a bromine, they will have a different J coupling constant. And in that case, what we expect to see is actually this pattern splitting this pattern. So we would get what's called a triplet of triplets. So not only do we have the signal associated with this hydrogen interacting with these two hydrogens, we're also going to have a signal associated with these two hydrogens introducing with these two hydrogens. So each of our 3 peaks, we get split into 3 smaller peaks. And typically what you'll see, if books are feeling really lazy, they'll just call it a multiplet. We would call it a triplet of triplets. If it were 1, we would call it a doublet of triplets or triplet of doublets, things like that. But basically you start getting these really broken up patterns. And they get kind of hard to describe as to what's really going on. But it's all the same effect. Because the angular momentum may be clockwise or counterclockwise for these two and for these two, that's going to have effect on the ultimate chemical shift of that particular nucleus. And again, what we're going to see is a statistical distribution of it. So that's why it gets kind of hard to see this, because you see one molecule and say, well, how can one molecule do all these things? It's not one molecule doing all these things. It's a mole of molecules doing all these things, and we're seeing a statistical average that gives rise to this. Now, something books tend to misrepresent, and I think Carrie is guilty of this crime. I'm not sure, but I definitely have seen other organic books guilty of this crime. They claim carbon-13 does not engage in J coupling. That's not true. It's misleading. So carbon-13 will undergo J coupling, but typically we don't see it. And the reason we don't see it is not because it doesn't undergo J coupling. It's because the odds of having 2 carbon nuclei next to each other is 0.01%. So of your whole NMR spectrum, 0.01% of it will see carbon-carbon J coupling. And typically what we see if we really zoom in on the carbon-13 NMR is there's little J couplings here or there across the bottom of the spectrum, especially if we have a really good signal. Now, J coupling is only limited to what are called geminal hydrogens. So, or not geminal, vicinal. Vicinal hydrogens. So what a vicinal hydrogen means is that each hydrogen is within 2 carbons of the other. So this one, 1, 2 carbons, so these will interact. This one, 1, 2 carbons, this will interact. When we get to 3 carbons, we don't see the J coupling. So beyond the second carbon away, we do not see any type of J coupling. So this 1H will not J couple with this 1H. There is a physical explanation for it. I'm not going to lie to you or make something up. I don't remember what it's called or how it works. But basically, their spin only goes out so far. It takes so much time for the effect of spin to move out, and it's not within the lifetime of the experiment. At least that's how it was explained to me. But that is J coupling in a nutshell. We use it to determine how many, so the way you dissect an NMR spectrum, there's 3 pieces of information. And this is for a 1H NMR spectrum. And I'm just making up a spectrum. I don't know what this corresponds to. The first piece of information is the relative ratio. So usually above an NMR spectrum, you'll see an integration curve. Integration just refers to the area of the curve, so you'll see something like 3, 1, and 2. The relative ratio tells you that based on the given number of hydrogens, these are their ratios. So they appear in a 3 to 1 to 2 ratio. Now this could mean that you have 3, 1, and 2 hydrogens, so you have a total of 6 hydrogens in the molecule, or it's a 6, 2, 4, so you have 12. You can have any multiple of this. Second thing it'll tell you is the number and types of hydrogen-containing functional groups. So since we have 3 proton peaks, we have three hydrogen-containing functional groups. And it kind of gives us the ratio of the hydrogens on them. But again, like if you see 3 distinct peaks, it tells you that there are 3 hydrogen-containing functional groups. This does not see oxygen-containing carbons. So something like a carbonyl, C double bond O, not going to be in there. The last piece of information that 1H NMR will tell you, and that's based on the splitting patterns, is the number of nearest hydrogens. So if we see a quartet, there's 3 hydrogens nearby. If we see a doublet, there's 1 hydrogen nearby. If we see a triplet, there's 2 hydrogens nearby. So that's why this is probably not made up, or why this is probably made up. So when we see a quartet, we know that this has 3 hydrogens on the adjacent carbons. If we see a doublet, this has 1 hydrogen on the adjacent carbon. If we see a triplet, we have two hydrogens on the adjacent carbon. If we have a multiplet, so let's say we have a doublet of doublets. Yes, I know that's really hard to see. It's also incredibly hard to draw. But if we have a doublet of doublets, this means that it sees 2 functional groups, each with 2 hydrogens. So the J coupling will tell us how many hydrogens there are on the vicinal carbons attached to this given functional group. So in principle, we can take 1H NMR and reverse engineer what the proper compound is. This is only true for very simple molecules, and we will quickly exhaust the number of molecules that we can actually do this with. What's done far more in practice is that you approach it with a guess. So if you go to nmrdb.org, they will actually have 1H and C13 NMR simulation spectra. So you can actually build the molecules, and it will give you the predicted NMR spectrum. Now, it makes a lot of assumptions, so it's not exact, but you can definitely start seeing these this J coupling effect. And I'll bring that up once I get done talking about J coupling and carbon-13 NMR. Now, carbon-13 NMR, unless you're using isotopically enriched molecules, you don't see this multiplet. The only thing carbon-13 NMR can tell you is the number of carbon functional groups and their relative ratios. Now, it is more powerful in that if we have a carbonyl containing, so a carbon double bond oxygen, or a carbon not containing any hydrogens, it will tell us that they're there, and we can use the chemical shifts to estimate what type of functional groups those probably are. The more powerful NMR, the 2D NMR, is called het core, heterogeneous core. So for het core, it will actually tell you how the hydrogens connect to those carbons. So a question just got asked, there are 2 carbon-13 chemical shift values that are very similar. How do we tell these apart if the relative areas are the same? The honest answer is that you really can't. They probably have a similar functional group. It's just a matter of what they're attached to. The only thing you're going to know in this case is that you have 2 carbonyl functional groups, and since they have the same area, those functional groups are in the same ratios. They're 1-to-1 ratio. So I think I answered your question this morning about the pre-lab. Someone's asked about pre-lab. The pre-labs are not done online. The pre-lab in your lab notebook, you need to do a title, a date, the purpose of the lab, the hazards, and you need to do a summary of the procedures. So let me bring up the Nmr Simulation Software. And this is actually pretty good software to work with if you're trying to see how to predict NMR spectra. So here I've drawn 3 carbons attached to a central carbon, simulate the spectrum, and we'll zoom in here. Now the nice thing about this software So it's telling you what the assignments are. So we've got a doublet here, and you see it says multiplicity is D for doublet. 4 here, it's saying it's undefined. It's 9 plus 1, so it's dectet. But you can see when we start getting these like really, really intense, like a lot of neighboring hydrogens, we start getting a lot of these really complicated splitting patterns. Now the other nice thing is that it will if you run your cursor over the hydrogens, it will stop that. It'll show you where they are. My goodness. They are for the spectrum. So when I highlight over these methyl groups, you see that's the doublet. When I run over the single hydrogen, it's showing you, the reason why it's not highlighting the whole molecule is because it's really just highlighting the chemical shift itself. Stop that. My goodness, you're being obnoxious today. Tell you what, we'll zoom out. So that's the hydrogen associated with that one. Now, if I want to go to something, make sure there aren't any questions. Show chart isn't due, but I would highly suggest you do it just because it's going to help you a lot with the data analysis. So here I've got, let's replace that hydrogen with a fluorine. Now, since none of these hydrogens here on the periphery don't contain a geminal carbon, we end up getting a singlet with area of 9. So we would only see one NMR peak in this case, and that NMR peak would correspond to our methyl groups, but the only thing we know is that we have one functional group that contains hydrogens. Now, if we switch over to the carbon-13 NMR, we actually see 2 peaks. Why are you doing this today? So we've got 1 peak associated with this fluorinated carbon, and this 1 peak associated with the methyl groups. Now they have a 3-to-1 ratio that tells us they appear in a 3-to-1 ratio. But if we look at our proton NMR, we only see 1 hydrogen containing functional group. So this gives us a clue in with the carbon-13 that there's actually more carbons in there than just hydrogen containing carbons. But that tells us then that we also know that we have a carbon or 2 that don't contain hydrogen on them. Other questions? There it goes. So when it comes to mass spectroscopy, there are a lot of different techniques, and we're going to focus on what's called electron ionization mass spec, or EI mass spec. Now, we have to make that distinction with electrical ionization EI versus chemical ionization CI. Why do we have to make that distinction? With electrical ionization, it's the equivalent of you trying to knock the electron off a molecule with a golf club. So you're going to hit it with a lot of force, and you're going to knock that electron off, but you're also going to hit the molecule itself, which is going to cause it to vibrate. So any molecule that's hit by electron ionization is going to fragment. Chemical ionization does not do that. With chemical ionization, we hit it just hard enough to remove the one electron, and so we only get what's called the parent ion. So as far as the molecule itself, we get intensity and mass over charge m over z. Each of these basically correspond to a molecular weight, because the charge here is +1, and there are techniques where we do look at +2 and +3. So that's why we have to use this m over z ratio. So for a mass spectrum, and let's just invent one. The most commonly used piece of information is what's called the parent ion. So what you're looking for is basically the heaviest or close to the heaviest peak. This is going to be the weight of the molecule that you injected into the mass spec. So in terms of identifying which molecule it is, that's typically what we do is we look at if you know what molecules could exist, we look at their molecular weights and we see which molecular weight corresponds to the heaviest parent ion. Now, the parent ion is not necessarily the highest, meaning like, you see I got a little dot drawn here to the right. We do have isotopes effect. So there's a possibility of having deuterium, there's a possibility of having carbon-13. So particularly for very large molecules, we end up getting like a leading peak. But as far as whether it's supposed to fragment, they all do that in electron ionization mass spec. Now, how they do it is different depending on how the molecule is connected. So we can definitely, this is what's considered a fingerprint for the molecule. If we had the fragmentation pattern, we can compare it to a database and directly identify our molecule. Now, there are ways to infer what the fragments are. They should basically correspond to different functional group units, and certain chains are more stable than the others. So the question you emailed me this morning, Abby, about the molecule, you're correct, because basically what it forms is a big aromatic ring. Now, you don't know what aromaticity is yet, but basically it will try to fragment in such a way to stabilize that +1 charge. Now, I'm also getting asked about IR spectra. So IR spectras are a tool for identifying a molecule. The big thing IR does is that it tells you what functional groups are present, and specifically it will tell you which oxygen-containing functional groups are present. So when we look at IR, we usually write it big box, we have absorbance, and we have wave number in verse centimeters. And there are different regions that correspond to certain functional groups as well as shapes. So about the 3,000 to 3,600 range. If we see a large shape like this usually indicates OH groups. Now, as I talk about in my video in IR, that's also kind of misleading because there are a lot of alcohols that don't actually have this peak. So when we say this, what we have is we have a molecule that engages in hydrogen bonding, and that's typically going to be your alcohols or your carboxylic acids. Now, very nonpolar alcohols like octanol, like long carbon chains that make them very nonpolar, you actually won't get this peak. It's only for small, really very good bases alcohols, ones that actually do the hydrogen bonding, that you'll see this. We have peaks that correspond to the different functional groups. So we have peaks that correspond to alkenes, alkynes, aromatic rings, cyclic molecules. So if you go underneath that test 1 table that's in test 1, or the exam tables that are in test 1, you'll get a list of bending frequencies that correspond to certain functional groups. So typically when we are looking at getting the molecule or identifying the molecule, we look for certain functional groups in the molecule that are very unique to that molecule. So if we want to compare, like, 2-propanol dimethyl-methyl ketone, well, the 2-propanol should have this big peak in it, whereas the ketone is not. So if we look at the infrared spectrum of what we measured, and we see this, we know we isolated the alcohol. If we don't see this, instead we see the peaks associated with the ketone, then we know we isolated the ketone. IR can't tell you what the structure is. It can only tell you what functional groups are present, and even then there's a little bit of ambiguity with it, because things like double bonds, well, it depends on the nature of the double bond. Are the double bonds next to each other? Are they in separate parts of the molecule? What are the orientations around the double bond? So again, you're mostly going to use IR to identify the functional groups that are in the molecule you're measuring. You're not going to use it to reverse engineer what the molecule actually is. There's too much ambiguity with that. Now, that said, what your books never talk about, beneath 1,000 wave numbers, we have what's called the fingerprint region. So the fingerprint region is actually unique to every molecule, or most of them anyway. So if you had access to a database, which we don't, actually we do, but we don't have a searchable database. If you had access to a database, you could take your IR spectrum and compare the fingerprint region to known molecules and directly identify it that way. So the same way that mass spec, the fragmentation patterns are unique to a given molecule, the same thing's true of IR. The fingerprint region is unique to a given molecule. So in practice with IR, we don't even really need to do this part. I mean, we would use this for rapid identification if we were trying to compare between molecules. But if we want to figure out what we'd have, we would look at the 1,000 range and compare that to known databases to see what we actually have. We just don't have access to what are considered searchable databases. So you take your IR and you compare it to a whole bunch of others. It can be done, we just don't have access to it. You either build it yourself or you pay for a very expensive subscription. Other questions? This is what I wanted to do earlier. This is what your nucleus does inside of a magnetic field when it's tipped 90 degrees. And much like in a magnetic field, you're going to notice it starts slowing down, or in this case, starts falling down. And eventually it's going to realign with the magnetic field. There you go. Ah. Review session for the test. We have the live stream, so if you want to do reviews during the live streams, we can, but we don't have a formal review session. And such a review session would have to be you asking questions. Now keep in mind with the analysis, mostly what we're looking for here is self-consistency. Is the molecule consistent with the spectrum? Or if we have two molecules, how would we use a given technique to identify which is which? And this is going to start showing up more when we start talking about the next tests, when we start getting into alkanes and we start introducing this idea of synthesis. Because synthesis on its own is pretty impotent. And I mean that because unlike Chem 1, Chem 2, where typically you only had one product, with organic reactions, especially when we start getting to like alcohols and alkyl halides, you can get lots of products for a given reaction. And what you want to know is, well, did you actually make what you intended to make? And if you didn't, what did you end up making? So we're going to need starting guesses. And typically what we're going to do with the IR and the NMR and the mass spec is say, okay, here's what you started with, here's the reagent, you know what the possibilities are, and this is what you ended up getting out. What did you end up making? So you kind of got a guess as to what you made, and you're going to compare those different guesses to the actual spectrum. So mass spec's a good one for this. If we have a hydrocarbon, something that just contains carbons and hydrogens, and we want to add chlorine to it, we can, but what happens is we typically get runaway reactions. So when we replace one hydrogen with one chlorine, it makes the next substitution easier and easier and easier. And so instead of getting one chlorination, we get di and trichlorinated products. Well, mass spec is really good for this because we can say, well, chlorine weighs 35.5 MU, so 35 and 36. Well, if we know what the parent compound was, we subtract off the one hydrogen and add the chlorine weight to it. We know what we should have gotten. And if we have anything above that, then we know that we got the di and the trichlorinated. Or if we want to get the dichlorinated, we just add 2 chlorines, remove 2 hydrogens, and we can figure out which of the products we got. Now, mass spec itself is a very easy technique to run, which is why it's so ideal for these types of reactions. The big problem with it is basically it doesn't identify functional groups. I mean, there is some information in the fragmentation pattern, but if you want a trivial way to identify a functional group, shove in the IR. So if you want to know if you made like the alcohol or the ketone, yeah, you could put it in the mass spec and look for differences in terms of 2 atomic mass units, AMUs or M/Zs. Or you can just put it in the IR and see, do you see an alcohol or ketone peak, or do you still just see a hydrocarbon? This will give you a lot of information. And this is what's done in practice. Usually a lab has at least an IR. Ideally it has a mass spec, and if it's a super rich lab, it will have an NMR. Those 3 are the trifecta for identifying a molecule. Not only can you tweeze out what you have, you can tweeze out the connectivities, especially if you have an unknown. And what we want to do in the lab, but we still haven't got the funding for it, is polarimetry as well. Now, polarimetry is also useful if you're working with chiral compounds. A lot of, full disclosure, a lot of synthesis is not chiral unless you go into pharmaceuticals. And even then, it's kind of complicated how you measure whether or not you've got the chiral molecule, because NMR will also measure chirality, and we can predict that. But again, trying to get you familiarity with these tools, not because you're going to be like predicting them based off of the molecule or trying to reverse engineer the spectrum to get the molecule, but rather to make sure the molecule is consistent with the spectrum. Because in practice, you do run these reactions and they just don't work, or it gives you some weird side product. Organic lab last spring, I had students that were doing a distillation and suddenly they had a black goo. Well, there was most likely iron contamination in the flask. It probably came down from the packed distillation column. You know, no one else was producing this black tar, so how do you figure out what you made? And this is where your analytical techniques will come in. Other questions? So there is a part in the notes that talks about combustion analysis. So when it says energy of conformation, basically if I give you a delta H for the combustion of a given molecule or a given constitutional isomer, can you tell me which one's most stable? So I think this shows up in that homework. It's also something that shows up in the study packets. I didn't have space for it in a discussion board, but it's definitely going to be a material that you're assessed on. But the idea is that can you tell from the combustion analysis what was the most stable molecule? Correct. Now, I definitely point this out in the notes. Don't get into the nasty habit of assuming that delta H and delta G are the same thing. This only works for organic molecules because they're always exothermic when they burn. So the more heat released, the less stable the molecule, because basically the heat that you're releasing is due to strained bonds. So when we combust a constitutional isomer being molecules that have the exact same chemical formula, they're just connected in different ways, they all finish up as CO2 and water. So the endpoint is the same. The change in energy is purely due to the stability. Now, if we treat the T delta S, so we have the Gibbs relationship, delta G, delta H minus T delta S. If we treat this term as basically being the same for a given set of constitutional isomers, which not perfect, but honestly not a bad approximation, we can rearrange this to get delta G plus D delta S equals delta H. And so the free energy change is related to the delta H. Since these are all basically the same, that T delta S is just a correction term. So if we take the absolute value of them, the reason why we would have a bigger delta H is because there's more heat or energy stored up in those bonds, and that heat or energy is due to steric strains, basically frustrations in the bonds. So if we take something like a cis isomer versus a trans isomer, they all combust to form 4 CO2 molecules and however many H2O molecules there are there, but they have a different heat release, a different delta H. And that's due to the fact that these two methyl groups press against each other, whereas these methyl groups are anti to one another. They're opposite each other. And because of that, they don't push on each other and there's less strain. But again, don't get into the nasty habit of assuming that delta H gives you information about delta G. And I say this because I have watched a lot of seasoned chemists make this false equivalency. Plenty of endothermic reactions occur. They're not unstable. So I think pointing out in the notes that this only works if we have an exothermic reaction, and it only works if they all have the same, if they're all constitutional isomers. If they're not isomers anymore, meaning that they don't have the same chemical formula, we get different different numbers of CO2 and H2O, and we can't do this analysis anymore. So something like octane burning versus methane, octane is going to have a bigger delta H, but it produces a lot more CO2 and H2O. So we can't really compare their stabilities, at least not by combustion analysis. But to answer your question, Camille, yes, that's really all you have to know. That's really the thing about combustion analysis. It's pretty straightforward. The bigger the delta H, the less stable. So you can see why I really didn't want to make a discussion board about it, because I would rather focus on the harder topics like NMR and mass spec. I think we also talk about hydrogen uptake. I think that's in the notes too. So amines are kind of like particularly, amines are anything that contain nitrogen, but specifically an amine refers to an NH2 group. Then we have primary, secondary, tertiary amines, which have different number of R groups, and then your amide and imides have different number of bonds between the nitrogens and the carbons. So if I remember correctly, the imide is a nitrogen double bound to one carbon and single bound to another. So that's why study guide answer sheet. Let me check the study guide answer sheet to make sure that's correct. But you are correct. Amines can refer to any nitrogen-containing compound. They can also, but within the amines, there are subcategories like the imides, the ilides, the amides. Like, there are a lot in them. And you have the imides as well as the ilides. Y'all have single bonds? It may just be a typo in the key. Wouldn't surprise me. Yeah, because those should be amines, because you've got primary, secondary, and tertiary amines based on the number of single bonds. That's when you start seeing the double bonds. That's when you start getting the hard to pronounce amine variants. Other questions? Yes, so it'll be used for basically helping you identify where the chemical shifts are and what the functional groups, what core functional groups correspond to which bending modes in the IR. So that'll be where you use in the upcoming exam. Again, you're not going to be asked to like derive a molecule from a spectrum unless it's a trivially easy molecule. Mostly you're looking for self-consistencies, and so you will have a molecule and you will compare it to the spectrum to see if it's self-consistent with that spectrum. But yeah, you're not to the point of being able to name these molecules, and again, this is far more reflective of what's done in practice. So you would use the chemical shifts to say, okay, I've got like a methyl group. The chemical shift should be in this range. If you look in the spectrum, you see a chemical shift in that range. You should be able to say, okay, I've got this molecule, I should expect to see this type of splitting pattern, and so forth. But the reverse is substantially harder and also not really done in practice. Except, again, for only trivially simple molecules. And you probably saw this with the study guide. There's one where I give you where you've got this molecule and versus this molecule. They give the exact same, they give very similar 1H NMR spectra. The fluorine doesn't really shift the CH2 groups far enough away from their given point to really distinguish between, oh, this is a CH2 group and this is a CH2 group adjacent to two bromines. So the only thing you can say from the 1H NMR is that, well, these two would basically give the same signal. But that's all you really need. You would do carbon 13 and, well, you'd do mass spec to figure out the difference between these two. All right, so it's 11 o'clock. I'm going to go ahead and sign off. Thank you all for showing up today. It was actually kind of nice to answer a lot of questions today. I have the live stream tomorrow, and I also have the live stream Friday. And I will see you all tomorrow. And again, I'll try to get the corrections to the worksheets, and also I'll take a look at this study guide to make sure, see if there's issues with the key as well.